Thanks everybody for joining us today for our next AAPG Salt Basins webinar. Today we're joined by Associate Professor Bruce Trudgill, who is a structural geologist from the Colorado School of Mines. Bruce has a BSc in geology from the University of Wales at Aberystwyth and a PhD in structural geology from Imperial College, where he worked with Mike Howard on structural inversion of sedimentary basins. Bruce has extensive experience in both field mapping and subsurface interpretation of salt structures across the globe. He currently lives at 9,000 feet or 2,740 meters above sea level in the Rocky Mountains, which serves as good acclimatization for fieldwork in the mountains of the Eagle Basin. So without further ado, I'll hand over to you, Bruce. Take it away.
Okay. Just going to share my screen, but thanks, Connor, for that introduction. And thank you for inviting me to give the talk today. So let me keep that up. I just need you to allow me to share and we'll be good.
Oh, okay.
I think that's you, Gabby.
If you could
Yep,
try
there you
again.
go. Yeah, got it.
Yeah, we can see your screen.
Okay, we all good? You can see everything?
Yes.
Yep,
Great, okay. So again, thank you everyone for joining wherever you are in the world today. It's morning here in Colorado and looking pretty cold and stormy outside, so I'm happy to be here to talk to you today about pre-Laramide salt tectonics in the Eagle Basin in Colorado. So what I'm going to do is basically present on behalf of my co-authors who are listed here on screen. So without further ado, let me introduce you to them. So this was a very intensive field-based study. So the students whose theses are available at the link at the bottom of the page to the Mines library. So if you want additional information on any of this, what I'm going to show you today, you can basically visit those theses that Wes, Haley, and Savannah produced. So Wes is sitting up here in the top left. He's on the outcrop at Red Butte, which we think is an overturned roof sequence on top of a salt wall. Haley down in the bottom left corner here is at the top of a log section of a collapsed conglomerate, basically at Bear Wallow Ranch near Newcastle. And let me try and understand why it's doing this. Okay, hopefully that will just go away. Savannah, basically in the field in the center here, in basically near Walcott, Colorado, and she's standing actually on an outcrop, basically, which represents the contact between the Triassic, where she's standing with her feet, and then basically the Jurassic Entrada sandstone is the unit that we think defines the end of salt tectonic activity out here. Picking up some background noise, I'll keep going. Okay, so one of the things that I want to start with before we get going here is that Ogden Tweeto, who is a true giant of Colorado geology, and he basically was the compiler of the first geological map of Colorado, which was published in 1979. And he wrote a paper which was published in 1977. And in that, Tweeto remarked that the thick upper Paleozoic sediments in the trough, he was referring to the Eagle Basin, between the uplifts consist in part of evaporite facies. Flowage in areas of thick evaporites began as early as late Permian time and strongly affected Permian and Triassic sedimentation, as well as later structure. So he identified that there seemed to be this influence of salt on this long depositional period in the mid-1970s, but that phase of long-lived salt tectonics was all but ignored then for 40 years or so. Of course, we have tools that Tweeto didn't have. Basically, back in the early 1970s, we have these fantastic models. So I'm just showing you an example on the left-hand side of some sandbox models from a paper by Ollie Duffy et al. In 2018. And here you can see shortening of salt structures, producing overturned flaps, shortcut thrusts, and basically these secondary welds. In the 3D diagram on the right-hand side, again, you can see nice three-dimensional views of pinched off salt diapers, basically now as thrusted secondary wells, etc. So we have these tools at our disposal, which allow us to basically get a better handle on what shortened salt structures look like. Here's another example from the Austrian Alps, basically by Granado et al. The salt's down here in pink, but again, you can see a pedestal feeding up into a welded feeder, and then with these secondary thrust structures and quite complex folds as well. The key thing with the examples I've just shown you is that both of these and many of the published examples are examples of thin-skinned shortening of salt systems. And we think in the Eagle Basin, we have something quite different. So let me take you to kind of a big picture view. So on the left-hand side, you've got a Paleogene sort of reconstruction of the tectonics of the Western US. And I just want to draw your attention to this large area in brown, which is the area covered by the Laramide orogeny, which extended from the late Cretaceous into the Paleogene. You can see the trend of the structures through here. And one of the key things that defines the Laramide orogeny is that it involves basement-involved thick-skinned folding and thrusting. So in contrast to the severe fold and thrust belt, which was thin-skinned back further towards the west. On the right-hand side, I'm showing you a cross-section drawn basically on the position of the green line. So from east out in the Denver Basin to west over into the Piceance Basin. And this is from Stern et al. In 2018, and it shows an interpretation of a quite strongly shortened system. You can see all the basement involved thrusts cutting up section. And this restores to give you about 80 kilometers of shortening. So the Eagle Basin will be sitting in this location here, in this area of quite strong basement involved thick-skinned deformation. So let me jump into the sort of Eagle Basin area. And again, to hopefully give people some reference, I'm going to start actually over towards the west in the Paradox Basin, which obviously is exceptionally well studied. We think we understand the salt structures out here pretty well from the field exposures and the subsurface data. So this would be Moab, this would be Durango down in the southeastern extent of the Paradox Evaporite Basin. This is the Utah-Colorado border running up through here. So this is a paleogeographic reconstruction by Ron Blakey at about 307 million years during a global sea level low stand. And the Paradox Basin is isolated as an evaporite basin in here, producing the evaporite sequences that we now see. If we shift though into Colorado, up into the sort of central belt of Colorado, and this would be Denver out here on the start of the Great Plains for a reference point at this time frame. This is the extent of the Eagle Basin, which is pretty much about the same size as the Paradox Basin. And I've outlined some towns in here for reference. Aspen in particular sits in the southern part of the basin. This is Eagle, and then Rifle off towards the west. So what you'll notice is there's the Uncompahgre Grey uplift, this ancestral Rocky Mountain uplift, which again was a basement chord deformation phase. We think that that bounds the northeast flank of the Paradox Basin as a flexural fallen basin. And then we have the ancestral Front Range Rocky Mountain uplift, which bounds the northeast flank of the Eagle Basin. So we think both of these evolved as flexural fallen basins, and the evaporitic deposits that we see were driven by glaciostatic variations at the end of the Carboniferous. So we think the system in terms of depositing salt is pretty similar. If I simplify that then a little bit, the Uncompahgre and Front Range uplifts defining the edges of the Eagle Basin with the Apishapa uplift down towards the southeast. Let me just briefly take you then to the Paradox Basin, because that's again a critical analog that we've been using. Again, you can see the extent of the evaporite facies outlined in gray, and I'm just going to show you three different cross sections: A to A prime in the northwest through the C to C prime down the southeast. And in blue are these northwest southeast trending salt walls that are well understood and well studied over in the Paradox Basin. So let's have a look at those cross sections. These are all drawn at the same scale. The top two are after Doling and Paz, and the salt is basically in pale blue in here. The bottom line cross section is after Escosa et al. 2019 in the Colorado part of the Paradox. So again, you've got a vertical scale bar in meters, horizontal in kilometers. And what you'll see is that the Paradox salt walls are generally fairly similar in size. The tallest structure is the Salt Valley Salt Wall, which is about 4 kilometers tall and about 5 kilometers wide. These features in the central cross section around 2.5 kilometers tall and 2 kilometers wide, and about the same on Gypsum Valley and Paradox Valley. And you can see flanking the salt walls, we've got these deep mini basins. We've got primary wells developed at the base of some of these mini basins. And then at the top, we've got a fairly thick progradational sequence coming off the buried Uncompahgre uplift, which we think was the driver for the growth of these passive salt walls over a period of at least 70 million years. So we think we understand this system reasonably well. So let me take you then into the Eagle Basin. So we're going to come into this central portion, and we focused on this because that's where the best outcrops are. And in other parts of the basin, we've actually removed all of the late Pennsylvanian through Mesozoic sections. So we don't actually have any exposures to work with. So I'm going to take you into this box, and I'll show you this map a number of times through here because it's kind of our composite map. It's taken from Tweeto's map of basically this Leadville quadrangle, part of the broader Colorado geological map. And we've simplified things, obviously, to try and sort of show you the main features of this salt system. So down in the bottom left, this is the ancestral Uncompahgre uplift in purple. The ancestral Front Range uplift is up in the northeast corner of the map. The gray lines coming down through here and over towards the west are basically where we interpret the edge of the evaporite basin. So the mini basins are color-coded on the right-hand side from basically the oldest, which are Eagle Valley age and late Pennsylvanian, all the way up through to the State Bridge of Permo-Triassic age. And I'll talk more about these ages and the distinct mini basins. So what you'll see if you look at the color coding is, in general, it seems that the older mini basins are down towards the southwest. And as we move into the center of the basin, we see progressively younger mini basins, with hard scrabble mini basin being dominantly Permo-Triassic in age. But I'll talk more about, how accurate that representation may be. But let me sort of take this map to pieces a little bit, because there's a lot going on here, and kind of break out the different components for you. So this is stripping everything away and just showing you the present day distribution of the salt tectonic elements in here. So the large area up in blue in here is exposed salt. This is Eagle Valley evaporite, as it's named, up at the surface present day. Primarily, we see gypsum with interbedded clastics and shales. We don't see any halite exposed at the surface up here, but we do know that that halite is present because we have a well. This black #1 well is critical. In the Eagle Basin, we have basically 3 key wells rather than several thousand wells that we have in the Paradox Basin. But this well is really important because it drilled through the section on the right-hand side in the Eagle Valley evaporites, and the logs basically show us that we have these repeated halite beds within the system. Quite similar, in fact, to the cycles that we see in the Paradox evaporites with this layered evaporite sequence. So that's a critical data point in the subsurface. We then basically have a large sort of northwest, generally southeast trending structure coming through the central part of the basin. I'll talk a lot more about that. We've interpreted in places where this is welded and where we feel pretty confident those are solid lines. We have more speculative welds as dashed lines, and where we're really stretching it, we have highly speculative welds which are buried beneath younger units, linking these things together. So if we now add on basically the components of the Laramide shortening and the Neogene extension, you can see how those overprint onto the salt basin. So this large area of the White River uplift brings basement up to the surface. All of our Carboniferous through Mesozoic is eroded off this structure. That's the Laramide uplift. We come down to the southeast, we've got the Sawatch uplift. Again, everything eroded off the crest, and that's also Laramide, but there's also a component of uplift associated with these blue faults, which are related to Neogene extension. The northern part of the Rio Grande Rift comes up through this eastern part of the study area. If you come over to the west, we've got some large Laramide structures. The Grand Hogback monocline is a fold that basically separates the Eagle Basin from the Piceance Basin to the west. That transitions into the Elk Range thrust, which is a thin-skinned thrust in the southern part of the Eagle Basin, and that then connects with this basement-involved thrust that I'll talk about later on the western edge of the Sawatch uplift. So going back to the sort of map and putting those things together, again, you can see now the mini basins as we've interpreted them, and the salt walls and salt wells separating those. I should point out that our erosion level varies a lot. In some places, like in these small mini basins, gypsum.0, we think we're looking at the very basal part of the mini basin. Nearly everything has been eroded, and we're only seeing the lowermost parts. So that adds to the complication in interpreting this. But let me take you to Wes's field area then, down in the southern parts. So Wes, his thesis was completed in 2019. And we focused down into the southern part of the basin, basically around Aspen, Colorado. But just as I mentioned with Ogden Tweeto at the beginning, we also built this on substantially on the publications of Bruce Bryant and his co-authors like Val Freeman, who worked at the USGS. And fortunately for us, all of Bruce's maps, notes, correspondence, field notebooks, and field slips, and I'm showing the example of one of the field slips here, are stored at the Denver Library of the USGS. So we're able to access those. And again, the detail on the field slips is astonishing. And I should also credit the fact that Bruce Bryant in the box down in here recognized one of these pre-Laramide unconformities, which we now relate to this salt movement. So he'd mapped these features just as we mapped them, but didn't have the tools, as I said, to explain them in terms of modern salt tectonics. So we built heavily on these maps. So this is the area that Wes worked in. So the town of Aspen is kind of down the southeast corner. And these are the 4 USGS quadrangle maps that he used. On the left-hand side, I'm showing you the stratigraphy in this part of the basin. We'll walk through that in more detail shortly. Okay, and just to show you that we start in terms of the major tectonic events, this is the ancestral Rocky Mountain uplift, generation of those associated fallen basins. We deposit the salt basically within the late Pennsylvanian, and salt tectonics then we think started pretty rapidly after that and extended for a period of about 100 million years through to the end of the Triassic. So let me put some details on this and show you some of these outcrops. So basically in the Eagle Valley evaporite, that's our main evaporite sequence sitting down here at the base of the section. And it crops out at the surface over fairly extensive areas. In some places, it's just a coarse gypsiferous breccia, like in Monument Gulch in this south of Aspen. Here we're seeing some bedded evaporites. This is layered gypsum overlain by caprock, and this is me, and then my colleague Thomas Heron. And Thomas Heron, along with Mary Carr, were instrumental in basically forming part of the examination committees for Wes, Savannah, and Haley. So I want to credit Thomas and Mary as well for all their help in getting these theses through to completion as well. On the right-hand side, you've got the Eagle Valley evaporite with bedded evaporite, gypsiferous breccia, and some plastic caprocks. So we have these extensive surface outcrops across the Eagle Basin. Jumping up section, I'll come back and talk about the Gothic and its equivalents later. We see the Maroon Formation. Again, this is defined classically by the maroon bells in the photograph here and Pyramid Peak, where you have this exceptional thick clastic sequence of late Pennsylvanian to Permian age. Again, fairly mixed in terms of the lithologies, but the key thing I want to outline is the large thickness variation we see. So we see thickness of maroon within the Eagle Basin from less than 500 meters to over 4,500 meters. So that's a pretty large variation. If we come up section then into the State Bridge, so this would be equivalent to the Moenkopi section in the Paradox Basin to the west, Permian to Triassic age, again, not well dated, any of these units actually. Mixed lithologies yet again, and again, a very large thickness variations. In some places, the State Bridge Formation is absent, so we have no outcrop whatsoever, and it's absent between the maroon and the overlying chinley. And then it's up to 1,500 meters thick. But we do have 3 distinct members that we can identify in the field, and that's crucial in terms of correlating between the mini basins. We come up then to the chinley, which is the upper part of the Triassic. And again, we have readily identifiable units, which allow us to correlate across the mini basin sequences. But again, a variable thickness range, but somewhat less extreme from 0 to 280 meters. As I suggested, this is because we think we're at the waning phase of salt tectonics. And once we get into the Jurassic, marked by an unconformity at the base of the Entrada Formation, we no longer see any influence of salt that we can identify. So let's take you in detail into the area that Wes mapped, and this is his map that he produced at the end of his thesis. It incorporates all the digitized strike and dip data from the published maps, as well as the hundreds of data points that Wes collected himself. And a couple of things to point out before I get into the details in here is, particularly if you look at the Woody Creek mini basin, this is one of the complications we have, because over in the east in here, we're actually seeing the base of the mini basin sequence. It's sitting on what we think is an evacuated primary weld down in here that separates the base of the mini basin from lower Paleozoic and ultimately basement units. So we're seeing kind of an oblique cross-section view through the mini basin here. But as we move up towards the northwest, we end up coming up to a flat-lying sequence. So we're seeing the top of the mini basin in map view. So this transition from oblique cross sections to map view is one of the complications in terms of drawing cross sections. Anyway, let me walk you through the features that Wes identified. And again, I'm skipping past a lot of the details which are in his thesis, and just show you all of the components which we think show that we have a very strong case, we think, for an early phase of salt tectonics. We have extensive evaporite outcrops. So those are outlined now in black, and they're linked by, in this case, a secondary weld along the Castle Creek salt wall. This would be then the primary weld at the base of the Woody Creek mini basin coming through here just north of Aspen. We've got another outcrop of gypsum to the north as a salt diaper up here. And then extending to the south, we've got a secondary weld, which ultimately is bounded to the east by basement. So we think this is a reactivated secondary weld as a Laramide thrust. I mentioned the maroon, and this broad area in blue in here is the outcrop of maroon. And again, this is where we identify about 4,500 meters, so in excess of 15,000 feet of maroon section through here. So vastly over thickened in this particular Woody Creek mini basin. We see abrupt thickness changes in the State Bridge. So as we come across this secondary weld up towards the north, the State Bridge abruptly thickens from 150 meters to the south to 730 meters within less than a kilometer. We also see pre-Laramide unconformities, which are adjacent to this interpreted salt wall structure. We see them up towards the north and also down towards the south. And I'll show you those in a little bit more detail. We see pre-Laramide growth faults. So these are fairly large normal faults that cut up through the section and show evidence of Permian to Triassic growth. And then, as I already mentioned, we think we have welds reactivated as Laramide involved basement thrust then in the southern part in here. So let me take you into this area that Wes mapped out in detail on the northeast flank of this Castle Valley salt wall through here, because this is critical. So now I've outlined, or Wes has outlined through here, basically the evaporite outcrops are outlined by these black dashed lines with a secondary weld linking those together. And the key thing is basically as you look in detail into here, so let me just again outline the maroon is in blue, and then the State Bridge is in this pale purple sitting in here. So we have a syncline which runs through the mini basin sub-parallel to the salt wall. And the dips in the State Bridge out here are pretty gentle. We've got a 5-6 degree dip into the syncline. They steepen up a little bit. And as we come into the maroon, there's a fairly low angular truncation as we come down into the maroon section. But these are still dipping off towards the northeast at maybe 30 degrees or so. But as we come in towards the edge of the salt structure, we go through the vertical, and then these overturn, and they overturn up to about 52 degrees overturn towards the southwest. As you move along strike, you still see that overturning, and as I come up into this northern area, we've got a really nice example of overturning within the maroon, steep dips towards the northeast, and then there's a fairly significant angular truncation now of 40 to 70 degrees between the maroon and the overlying State Bridge. But as we move away from that salt structure off towards the north, off this map, we no longer see that angular unconformity. So we think this is pretty strong evidence for something that's happening pre-Laramide, and we equate that to drape folding, halokinetic drape folding on the edge of the Castle Valley salt wall through here. So let me show you a photograph. This is one of Wes's field photographs. We've got the evaporite outcrop down in the bottom left corner, labeled as PE. So as we move towards the northeast, we're coming into the mini basin sequence. This is all overturned maroon through here, which gradually becomes very steeply right way up. But if you project in then the base of the state bridge, this is coming through with that abrupt angular truncation. But as we move away, as I mentioned, we lose that angular truncation between the sequences. So here's kind of a sketch of that relationship. And we think we have pretty good analogs. This is just one from Iran, basically where we have upturned halokinetic drape folded halokinetic sequences within about 200 meters or so of the edge of this particular salt diaper in Iran. And we think we're seeing something pretty similar here. So let me show you a couple of cross sections, which I think emphasize this early phase of halokinetic deformation along the Castle Creek salt wall. Again, Wes built 5 cross sections through here, and I mentioned already the complexities of building cross sections and also restoring those. But luckily, we were able to use Global Mapper's software to build our initial framework for putting all of the data points into a 3D reference frame. So we thank Blue Marble Geographics for the donation of that software. And then we also used Move donated by Petroleum Experts to basically do the reconstructions. I'm not actually going to show you any of the reconstructions today just for the sake of time, but again, they are within all of the theses. You can see the reconstructions that were constructed by each of the students. So I refer you to those. So let's take a look at cross-section A to A prime for this northern part of the region, transecting across this Castle Valley salt wall from the Snowmass mini basin on the southwest to the Woody Creek mini basin to the northeast. So here's where this cross section, again, the maroon's in pale blue, the state bridge is in this pale pink purple color. So here's the interpretation of the salt wall structure. It's pretty narrow through here because it's been contracted during that Laramide shortening phase. But on the northeast side, again, just to highlight, we have these overturned dips, which then become right way up. And as we move out away from the salt wall structure, eventually we just see a conformable sequence from the maroon into the relatively flat-lying state bridge. So this would be a state bridge thickness of about 1,200 meters. We come onto the southwest side. We don't see any of those steep dips. We see a relatively flat-lying state bridge and a fairly isopachous section sitting above that. So a fair sort of asymmetry as we come across this particular salt wall feature, particularly during maroon times. Move down to cross section B to B prime in the southern part of the area, just south of Aspen, and this highlights a couple of other features that we're going to see down here. So within this area, this is basically cross section B to B prime from the west southwest to the east southeast. So it's picking up these normal faults that basically Wes is interpreted on a cross section through. And again, I just highlight the fact that the faults have several hundred meters of throw, and we increasingly see thickening, particularly in the state bridge, the pale pink purple colored unit down here as we come into the hang wall. So we think this is strong evidence that these are Permo-Triassic age growth faults. And again, you can see how that state bridge sequence of the lower part thickens substantially as we come off towards the east. And then we get into this abrupt overturning of the lower part of the state bridge and the maroon, and then up against the basement off towards the southeast. And this is where we'd interpret a secondary weld, which is now a basement involved thrust structure. If I get a little bit more speculative and remove the strat column at the bottom, we can extend the cross section downwards. It is getting pretty speculative because we're having to project sort of the base of the salt from a large distance off towards the south in this case. But we think we have these thick mini basin sequences in the maroon. This would be our Gothic sequence, so just above the salt at the base of the mini basin. And then interpreted as being welded out with the large normal faults then detaching on top of these salt rollers sitting down at this deeper level. As we move progressively then over towards the east, here's what we'd interpret as a maroon, excuse me, mega flap coming steeply then at the flank of this interpreted secondary thrust weld. So the lower part of the maroon sequence basically is subvertical to overturned, coming up to the flank, forming this large mega flat type structure. If we move a little bit along strike, I can then show you the critical relationship, and this is the one that I mentioned that Bruce Bryant mapped basically on the USGS quadrangle maps and showed very clearly in his field slips and notebooks that that overturned sequence is then truncated in the upper state bridge. So the chinley in here just above that is flat lying and truncates these severely overturned dips. So this must be a pre-Laramide unconformity. And again, we interpret that it's the result of halokinetic drape folding up against this now long gone salt wall, which is now only present as a secondary weld with the upthrust basement sitting over here in the hanging wall towards the east. Okay, so that's kind of the southern part of the basin. I'm going to take you into the central part of the basin, up around hardscrabble. So let me just show you that we do have a handful of seismic profiles through the Eagle Basin. They're fairly old 2D profiles, but hopefully we can basically see some details from that. So if I put basically the seismic profile across hardscrabble through here. So south is off towards the left and north. It actually almost ties into that black #1 well that I mentioned. So we think we have a pretty thick salt sequence up towards the north in here in the Eagle River salt wall. This would be the Gypsum Creek salt wall, which I'll show you in more detail shortly. And then this would be the hardscrabble mini basin, which is dominated by a very thick state bridge sequence in here. The maroon is actually relatively thin and about 500 meters, and the state bridge is hugely expanded to about 1,500 meters. So seemingly a very different age for this mini basin than the ones I was just talking about. So this is the area that Savannah basically worked on for her master's thesis published in 2021. So she focused on hardscrabble mini basin, Bellyache and Walcott off towards the north. And you'll notice the color coding here is suggesting a variety of different ages. And I'll show you why we think that particularly hardscrabble, which is the one I'm going to focus on now, has an early phase developed during the Eagle Valley, the late Pennsylvanian, of basically salt tectonics and halokinetic drape folding, then a thick mini basin sequence, which is much younger in that Permo-Triassic state bridge formation, excuse me. So let me show you one of Savannah's regional cross sections. So the salt is in this paler purple color here. Again, I've labeled up this as the Eagle Valley evaporite. The cross section line, this again is Savannah's map, but maybe it's a little easier in this context just to show you where the cross section comes on the large scale map down in here. So it's coming from just north of Wes's study area and the Woody Creek mini basin. We're going to clip the edge of that, running across Red Table Mountain, then out towards the north. So here's that Gyp Hill salt diaper that separates the Woody Creek mini basin to the south. We then come through the Red Table Mountain mini basin, which has a thick Eagle Valley formation, which again is the unit directly above the salt, equivalent in age to the Gothic formation I mentioned earlier. And then a thick maroon mini basin through here, okay, in the Red Table Mountain. We come across the Gypsum Creek salt wall, and things change pretty dramatically. We have a fairly thick Eagle Valley formation, as I mentioned, the relatively very thin maroon, and then this very thick state bridge sequence showing the dominance of that Permo-Triassic age for the central part of the mini basin through here. As we keep going off towards the north, things change again. Again, the age of the mini basin sequences shifts as we cross the Eagle River salt wall and end up back in the Walcott mini basin off towards the north. So let's zoom in and focus in on the edge of the hardscrabble mini basin, because this large mini basin sitting in the center of the Eagle Basin is key, and particularly the exposures that Savannah mapped along the southern edge of the mini basin and along the northeast edge of the Gypsum Creek salt wall down in here. There are no published maps in this area, so this is all mapped from scratch in this case. And particularly I want to focus in on the relationships right on the edge of the Gypsum Creek salt wall in here. Again, I've already mentioned that over-thickened state bridge, so we think this is the main phase of evacuation and accommodation creation in the mini basin, but I'm going to take you right into the edge of the Gypsum Creek salt wall in here. And this is where Savannah was able to map out what we interpret now as the halokinetic sequences, which are developing by drape folding on the flank of the Gypsum Creek salt wall. So Savannah's map is over on the right-hand side. So the salt is basically salt wall structure is down on the southern edge in here, and we're going to basically come into this area where we see in the Eagle Valley Formation in this dark purple unit, this halokinetic drape folding. Again, the maroon in here is pretty thin, and then we rapidly come up section into this relatively gently dipping and ultimately almost flat lying state bridge towards the top of the mini basin. But in these basal sequences, we see something quite different. So here's the Eagle Valley Formation. This is exposed in a very steep forested slope in here, but with a fair amount of struggle, you can get up to these outcrops. And the key thing within these beds in here as well, a couple of things to point out, first of all, is one is that we have at the base of these sequences, these are quite coarse sandstones. They have a coarse breccia towards the base, which contains fragments of what we think is reworked Eagle Valley evaporite and also Eagle Valley Formation. So we think we're seeing some localized reworking coming off the Gypsum Creek salt wall. And you can see the dips are annotated in here. We go from 69 degrees right way up to 80 degrees overturned and 64 degrees overturned in Eagle Valley Formation. As we come up into the maroon, though, these are right way up and dipping at about 30 degrees back towards the north. So now we have an unconformity much earlier than the one I was showing you in Wes's study area between the Eagle Valley Formation and the maroon. Let me just show you a field shot of what this looks like. So this is Savannah out in the field on a sort of classic Eagle Valley outcrop where you're struggling to stand up for more than a minute or so on this slippery surface. But we're about 200 meters basically into the mini basin from the edge of the Gypsum Creek salt wall. So this is Eagle Valley Formation exposed on this ridgeline, and it's clearly overturned at about 85 degrees in this location. But as you basically move out tens of meters, no more than that, into the mini basin, we actually get to being 34 degrees right way up. So we think we're in this sort of location. So this is a figure from Rowan et al. 2003 defining these halokinetic sequences and then these composite halokinetic sequences. So we think our location in the photograph on the left is somewhere just in this red box where we're seeing this change from localized overturning right up against the flank within 200 meters of the salt wall to rapidly coming back to being right way up. So we think pretty strong evidence for halokinetic drape folding. Okay, so finally, I'm just going to take you out to the far western part of the Eagle Basin into what we've generally called the Rifle Falls mini basin, but we think it may be more than one mini basin we're digging out here. And this is from Haley Thorson's master's published last year, 2022. So in this region, we see again something quite different. We're on the edge of the White River uplift. We do have some fairly extensive outcrops of Eagle Valley evaporite in blue, but you'll see that we're identifying that most of the interpreted mini basin and salt-related mini basin deformation is occurring within that earliest phase in the Eagle Valley, Lake Pennsylvania units. So just to simplify things, I'm going to put this map up, which is after Scott et al. 2002. So this is the town of Glenwood Springs on here, which sits on I-70. So if you've driven out from Denver to the Paradox Basin, you'd have driven through Glenwood Springs. And what Scott et al. Identified in black in here is these outcrops of the Eagle Valley evaporite. You see they're scattered along the edge of the White River uplift, which would be up towards the north. So I'm going to basically take you into two areas that Haley mapped in detail, the Bear Wallow salt wall in this red box over here towards the east, and then in the far west of the area, we're going to go to the Puma Paw salt sheet and show you something quite different in the final exposures. So these are Scott et al. Cross sections, and Haley's produced a series of cross sections which do look a bit different to this. There we interpret the salt tectonic history somewhat differently, but these outline the general shapes of the Bear Wallow salt wall in here, which I'm going to show you first, and then what we now interpret as the Puma Paw salt sheet in cross section. But again, just to emphasize, we are on the edge of the White River uplift. We do have some significant Laramide deformation in here, which we have to basically initially take out from before we can basically restore the salt geometry. So again, those are included in Haley's restorations in her thesis. So this is Haley's map basically of that Bear Wallow area over towards the east. So just to color code you again, this pale grayish purple unit in PEE is the exposed salt as these gypsiferous salt wall structures exposed at the surface here, and then also over up towards the north. In the bright purple color, this is the Eagle Valley Formation, so just above the salt, and then the maroon again is blue. And one thing to pick up on here is if you look on the south side of the salt wall structure, which would be running northwest, southeast through here, you can see we have these very substantial overturn sequences. Okay, Haley actually logged the section through an overturn sequence down in here, and the red line through the maroon. So this area in here is overturned, but locally it shifts very abruptly to being right way up. So all the way along the edge of the Bear Wallow salt wall through here, we keep switching from being overturned to locally right way up, and then switching back to being overturned again. The other thing that's somewhat unique to this area is the outcrop in yellow labeled TCC is the Canyon Creek conglomerate, which is a 400-meter thick conglomerate, which we think is sitting on the crest of the collapsed salt wall. But this is the much younger feature, which I'll talk about in a second. And again, Haley logged that whole sequence through that conglomerate. So these are Haley's cross sections just in this area. She drew 7 cross sections, and I'm now showing them in a 3-dimensional view. So starting off in the east, we think the whole of this Bear Wallow salt wall is actually welded shut in here in the secondary salt weld. But again, to emphasize, if you look in the maroon and the Eagle Valley Formation purple, we're strongly overturned here. We move along strike, and then we become right way up before going back to being locally overturned, back to right way up, and then overturned again. On the north side of the salt wall, where beds are consistently dipping moderately steeply to the south and right way up. So here's Haley standing then. I mentioned that collapsed conglomerate. She's basically standing now looking off towards the east. So we're on the crest of the salt wall, and this is the conglomerate that's folded into a V-shaped growth incline through here. So what we think is that the salt wall was exposed post-Laramide in the Neogene, potentially. The salt wall structure then started to collapse, and we accumulated this thick, coarse-grained conglomerate in this V-shaped incline on the crest of that structure. And that's shown again in one of Haley's cross sections through here. I'm just going to flick that cross section around so it corresponds to the view on the left, with north to the left and south to the right. So here's the conglomerate sitting on top, what we think of now this collapsing salt wall. And again, here's that local overturning. So what Haley sketched out in here is we think that local overturning is associated with flaring along the edge of this Bear Wallow salt wall. So locally, the diapher basically flared out with an extrusive tongue potentially, and overturning of those mini basin sequences beneath that. The key thing here is that we don't actually have any outcrops though of what we think might be a salt tongue. For that, we have to go over to Puma Paw, which is the far western extent of the area. So on the left now is Haley's map of the Puma Paw salt sheet as we're now interpreting, and this is pretty complicated, and this is where we do diverge pretty strongly from the published map in here. So Haley has a lot more strike and dip data, a lot more structural data, and we've remapped the position of the salt. So the salt is in, again, the pale purple gray, and you can see it's now in these sort of discrete outcrops sitting through here. So Haley's got 5 cross sections. They're in the 3-dimensional view. We're looking from the east towards the west now, so north is towards the right. And things again get pretty complicated. We've got local overturning on the southern side, just like we saw in Bear Wallow. But what's just appearing now in these cross sections of these shallow salt sheets, which are now sitting on top of the Eagle Valley Formation. So we have stratigraphically older Eagle Valley evaporite sitting on top of the younger Eagle Valley Formation. So the way to really try and understand this, I'm just going to show you 2 photo panoramas. So the first one is going to be taken standing on cross section D2 and looking back towards the east at cross sections D to D prime and D1 to D prime. So this is where things start to get pretty complicated, and we spend a lot of time scratching our heads sitting on outcrops out in the Puma Paw Ranch in here. But here's what we think is going on. So I'm going to start over to the north. So this would be the White River uplift, where the pre-salt section steepens in terms of the dips, and they come subvertical in here. So this is basically pre-salt section, which is subvertical. We then have exposed in this area in purple with the dots, what we interpret as an autochthonous salt breccia. We have no gypsum exposed within this unit, but we have very coarse clastic blocks of sandstone and limestone in an irregular breccia through here. And we think this is basically the remnant autochthonous salt level. I'm actually going to jump over to the southern end because, again, this is now showing the upper part of the sequence, which is dipping very gently. So in the post-maroon, we see no effects of the complex geometries I'm now going to walk you into. But as we come into the maroon, so coming down section, basically from the south, this is the upper maroon. These beds are now dipping at 85 degrees right way up. Remember, these beds up here in the upper maroon and younger are basically dipping at maybe 10 degrees. So we see a steepening as we come down section, and the lower part of the maroon actually overturns at 60 degrees. We then have what we interpret as a subvertical salt feeder that feeds up onto the crest of this ridge and then into the ridge on the back, and then rolls over into this salt sheet. So we're seeing the continuity from the feeder to a salt sheet, and the salt is climbing up section to sit on top of this folded Eagle Valley formation. And that's what we're seeing then on this ridge line in here. This is an erosional remnant of the salt sheet. So this is Eagle Valley evaporites sitting on younger Eagle Valley formation. And our interpretation is it's climbing up section back towards the north. In other words, back to where it actually came from, which is pretty bizarre. Okay, so finally then, let me show you one last panorama. So we're basically now going to shift and look towards the west. So we're going to stand on cross-section D1 in the far east and then look back towards the west. So this is a photograph I took last fall, and again, it's pretty complicated. Hopefully what I can do is show you that this is the ridge line I was just pointing to. This is D to D prime coming up through here, but we're now looking to the west. The south is to the left and north is off towards the right, but we're seeing the same features. Here's the right way up maroon overturned. Here's our subvertical feeder, the folded Eagle Valley formation. And again, you have to sketch in that this salt feeder would then feed into the salt sheet, which again almost reaches, ironically, the steeply dipping autochthonous salt breccia through here. I'm standing on top of basically this subvertical feeder on the ridgeline for the photograph. So the last photograph was taken looking towards us, so on top of this same feeder. So on the ridgeline now in the background, Haley section D2 to D2 prime, here's the same feeder, which is only about 15 meters wide in here, but it's not welded out. And then here's the dissected salt sheet basically sitting out on these ridge lines. So this would be the same salt sheet, it's just now we're seeing those erosional remnants. And again, just to point out that as you work your way up through the maroon, it goes from being subvertical to very rapidly, those dips drop down to about 30 degrees to the southwest. And then again, here's that post-marine sequence unaffected by these complex salt geometries dipping gently off towards the south. So hopefully I've given you a kind of a whirlwind tour through the Eagle Basin, but we do have a number of questions that we're still basically trying to grapple with. We're still not sure on what sort of basement controls there may be on the salt wall orientation. It seems significantly more complex than the northwest-southeast trends that we have in the Paradox Basin, but partly that could be due to the Laramide overprint. We have a hypothesis that the mini basins get younger in terms of that fill. The primary fill and accommodation creation seems to get younger into the center of the mini basin, but I've just been showing you that we also have evidence of very early development of salt sheets in the western part of the basin. We're still trying to correlate surfaces between the mini basin, and this is where my colleague at Mines, Dr. Mary Carr, who also generously gave up her time to help in terms of advising and serving on the committees for all the students, is helping us in terms of trying to think how we can correlate potentially some of the aeolian units between the mini basins. And as I've just shown you, the extension of the Eagle mini basin towards the west is pretty complicated, and we're still struggling to understand why it's so different. Is there some much stronger sediment flux into this basement, this part of the basin really early, which triggers this early phase of allochthonous salt development. And we've also got plans in the future. The Eagle Basin extends off towards the southeast over the Saguache uplift, and then we start seeing outcrops again in South Park. So that's where we're headed next, towards the southeast and the South Park. Again, as you might suspect, I'm a little concerned about the quality of the field assistance we may end up with when we get into South Park, but obviously we'll deal with what we have. So finally then, just again to thank you all for your time this morning and for basically spending time with me in the Eagle Basin. If you've got sort of longer term questions, please don't hesitate to contact me through email. Again, this photograph is on Puma Pool walking out at the end of the day, and I'm sure many people who've worked in salt basins have had the experience of rage against the dying of the light, as yet again we end up trying to map in the dark as we work our way out. So again, thank you for your time, and I'm happy to take any questions. Stop my sharing.
Thank you so much, Bruce, for this excellent talk. So yeah, that was really enlightening to see a bit more of the geology of the Eagle Basin area. We have already some questions in the Q&A session. If you have to answer.
Yep. If you want to read them, then I can think about an answer.
So from Celine Chaker, how can we differentiate between salt wells and walls in the field?
Salt wells and walls?
And walls.
Yeah, so I guess we're defining a salt wall as any of these basically original salt wall structures, so elongate salt diapirs. So in terms of our definition here would be we distinguish between a wall is where we still have remnant salt. So for instance, that feeder that I was just pointing out in the Puma Pool area, we can still clearly see that there's remnant salt in terms of gypsum preserved along that. Technically, if it's going to be a well, then we've evacuated all the salt from between those surfaces. But as you know, Gabby, wells are more complicated than that. And again, we can locally have material entrained along that well. So again, we can distinguish wells in the field where we think we've lost all of that salt. But obviously, when we get into a seismic domain, it gets more complicated. But in the field, we're defining a salt wall rather than a secondary feeder where we still have salt basically clearly along that feature.
Okay, thank you. Yeah, exactly. As you mentioned, sometimes it can be a bit complex. For example, in Morocco, we see a lot of basalts from the Triassic camp remaining in the surface of wells. So next one is from David Lenke for Bravo. He says, great to see your work and what your students have been doing. It will be fun to see further comparison to time equivalent horizons in the paradox. And yeah, looking forward to reading the thesis. He says so. Comment from him. Then from Mark Rowan, great job, Bruce, as always. And given the variable outcrop and the lack of holokinetic sequences in some areas, how do you distinguish between one very long original south wall, locally welded, and two or more diapirs linked by steep faults? For example, between Snowmass and Wood Creek mini basins.
Yeah, no, that as ever, Mark, that's a very good question. Yep, there are certain places where we are interpreting continuity along strike between some of these features. And yes, there's definitely places where you could interpret them as somewhat separate, linked by fault structures rather than in continuity. Again, in the area that you're talking about, in the Woody Creek, again, I'm gonna have to dig and think in more detail in terms of what West mapped through there. But we do see generally a fairly consistent, the overturning within the maroon section, which I've walked you through on that northeast side of the Woody Creek structure, is pretty consistent all the way along the edge of that structure. So, and again, it's the same in the area Haley was working on, the Bear Wallow. Again, you're always seeing that very abrupt steepening. Okay, sometimes it doesn't completely overturn. So I think we can say that we feel reasonably confident that there was some continuity through there, but I do take your point that the level of exposure doesn't allow you to maybe make the same correlations you'd be more confident in doing in the paradox.
Yes, thank you. Then we have a question from Adeleke Ajobe. And thanks for the presentation, Bruce. I was wondering if salt wells have any sealing integrity. If so, would salt wells provide sealing capacity for CCS reservoirs and also for oil and gas? What's the lithological composition of salt wells?
Well, that's a critical question, and Gabby, as you know, since that's exactly what you're working on. I always say that, again, some of the people in the audience may remember, and again, I'm winding the clock back now, probably 20 years or so. I think there's a talk at AAPG one year, which is entitled, "Do Salt Wells Seal? Yes, no, maybe." And I've done extensive amounts of work in the Gulf of Mexico, and other people on this call obviously have as well. And I think we're still at that point where we have examples where, yes, we can seal across salt walls and some of the wells that are drilled in the Gulf of Mexico, so that very clearly in terms of the pressure differentials, etc. But predicting whether they seal, I think, is a lot more challenging. So yes, they can definitely seal, but it's the predictive part that is really, really difficult. And hopefully it's what people like Gabby, this is hopefully you'll have some answers where we can hopefully make some better predictions as to when they seal and when they don't, but they certainly can.
Yes, yeah, I agree. That's a complex question, and it depends a lot on the original stratigraphy of the basin and how heterogeneous the evaporite sequence was as well. So yeah. Next one from James Granat. What are the class types in the Canyon Creek?
So the Canyon Creek conglomerate basically is pretty coarse-grained. Again, we see almost no clear grading within that unit. What we do see, again, is a pretty strong variation in class type. Primarily, they're actually coming from the lower Paleozoic section. So that will be in the pre-salt, which, if you remember, is exposed on the edge of the White River uplift. So what we think is happening is basically it's unroofing, if you like. We're stripping off that lower Paleozoic sequence and then dumping it into these collapsing synclines on top of the exposed salt walls. One of the things that suggests that, Jim, just in a general sense, is that when we looked at the class content, it did seem to be and again, I'm pushing this a little bit, in a general sense, an unroofing type sequence. In other words, the younger part of that lower Paleozoic sequence is dominant in the lower part of the conglomerate, and the oldest part of the lower Paleozoic sequence seems to dominate in the upper part of the conglomerate. So we think it's unroofing lower Paleozoic sequence off the White River uplift.
Yes, thanks, Bruce. So we have one more question from Mark Rowan. He asks, he says, I don't understand the relationship between salt sheet and the autochthonal salt. Can you please explain what you think is going on? And could the salt sheet be part of the LLES, I think the layered evaporite sequence?
I'm thinking. Yep, I think we too, Mark, struggle with that relationship. I don't think the salt sheet is part of the layered evaporite sequence. It seems to be, and again, I try to show on the photographs that it seems to be cutting up section across the underlying Eagle Valley formation. So there is a possibility, yes, that it's part of that Eagle Valley formation sequence. But yeah, the relationship with the underlying autochthonous layer is challenging. Again, that autochthonous layer is interpreted partly because of its stratigraphic position. It's sitting where we'd expect it to be sitting, if you like, just above that lower Paleozoic sequence. And again, it is comprised of this very chaotic breccia. Reminds me of some of the things that obviously you're very familiar with from South Australia and the Flinders, and that Thomas worked on in detail. I guess the thing I'd say that is pretty clear is that we can, excuse me, we can tie that feeder that I showed you into the salt sheet on a couple of those different ridge lines in continuity. And there's a very clear discontinuity between the feeder and the Eagle Valley formation that it's cross-cutting as it basically goes up section. Again, it's got overturned maroon on one flank, and it's got a high angle truncation against the Eagle Valley formation on the other flank. So we think we can tie the feeder into that interpreted salt sheet. Again, what's sort of baffling is, that feeder can only be maybe 300 meters tall at the most. I mean, the autochthonous salt layer is pretty shallow beneath that. So why it's basically, doing this so early in the basin history, which we don't see anywhere else, is challenging. And I absolutely admit right up front, there are potential different interpretations for this pretty complicated feature. Because again, it's folded then during the Laramide. So you have to unwrap that Laramide folding. And even more confusing is that the Laramide folding is much stronger to the north, and then it dies out effectively, or flattens out, I should say, to the south. So some parts of the sequence I was showing you are pretty strongly affected by Laramide folding, and other parts are not. So that makes, the restorations pretty difficult. But no, I accept, that relationship is still challenging us significantly.
Yeah, great. Thank you. Then we have a number of greetings from lots of people. Giovanna Rebelo, Oscar Fernandez, Tinduli. Then we have a question from Haseb Ahmed. What's more complex, halokinesis or tectonic deformation? I don't think I quite get the question, but I think he mentioned halokinesis or general tectonic deformation.
I think it's a general question. I think, salt tectonics, one of the reasons we're all here, right, is kind of it's the most challenging, I think, if, in terms of understanding a tectonic system, when you've got a rock unit that basically is deposited in one place and can move pretty dynamically to somewhere else over geological time and then disappear completely. That makes it pretty challenging. It makes it really challenging in terms of the restorations that we're trying to do. So yeah, I think it's kind of the ultimate challenge, I always think.
Excellent. And then we have some more greetings from other people. Mohammed Amer saying Shakar, Gary Henson here from Zero, and James Granat again saying thanks, and Thomas Hiram. So if there are any other questions, please feel free to put in the chat box. If we don't have any other questions, then we'd like to thank you very much, Bruce, for your talk, and everyone in the audience. If there's any further questions, then please feel free to email us. We might forward to Bruce to answer later on. Yeah, and then
any follow-ups.
Thank you, and then hopefully the recording of this webinar will be soon in our channel.
Okay, well, thank you, Gabby, Connor, Nawaz. I appreciate all the work you're doing.
Thank you very much.
And putting this together and putting these talks. I think they're hugely valuable for all of us. So again, thank you for all the work you're doing.
Thank you.
Thank you very much.
Bye, everyone.
Cheers. Take care all.